Okay, we're going to actually do this problem in 2 steps. I'd like you to first work down just through step 1 where you determine the electronegativities. After that, we're going to go ahead and do the rest of the structure. So go ahead and pause the video and look up those electronegativities. Okay, let's take a look. So you can see here that fluorine is going to be just short of 4, 3.98, and our silicon is going to be 1.90. So for silicon, 1.90. For fluorine, 3.98 or 4, whichever one you want to write it as is fine. So what's our delta En there? Well, look at that. Our delta En is actually going to be 2.08. So this is bigger than our dividing line for what we said was going to be an ionic species. However, it's also very close to that dividing line. So the way that these things work, we're going to use some hard and fast rules in our class to make things simpler. But of course, reality tends to be more complicated than the textbook. So what would you really do? Well, instead of just focusing on delta En in the real world, you'd run and you look at lots of physical properties and you would decide, does it act more like an ionic substance or more like a covalent substance? And it turns out that it actually acts like it's a polar covalent substance for each of the individual bonds. The molecule itself, we can't say anything about its polarity yet because we aren't inflating it into 3 dimensions. But right now what I will point out is despite delta En being high enough to call this ionic, we're actually expecting it to be a polar covalent bond. So for the nomenclature, we'd use our rules based off of covalent molecules, so silicon tetrafluoride, as opposed to the ionic rules, which should be silicon fluoride. So, silicon tetrafluoride. Now that we've determined our electronegativities, go ahead and work through the rest of the problem. Pause and do it now. Okay, so let's set this up. Our small electronegativity atom goes in the center. We'll space out our other atoms all the way around it. Silicon, fluorine, fluorine, and fluorine. Now we're going to total up our valence electrons, or our octet electrons. So we're going to have, let's see, 7 for fluorine. So here's how I like to table these up. Fluorine has 7. Silicon, remember, carbon-based life, silicon-based life. That's going to remind us that it's going to have 4 electrons. The reason that they think that is because silicon-based life, they think that could exist since it has the same number of octet electrons as our carbon atom does. I think it's debatable. So we have 1 silicon, we have 4 fluorines. Multiply across, that gives us 28 fluorines plus 4 more from silicon. We have 32 electrons to place. So 32 electrons. Now we're going to draw a single bond between each of them. And from here, I'm just going to start counting as I go. So it's going to be 2, 4, 6, 8. Use up the remaining. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. And notice when I did that, I kept just placing them all over the place, but I did 2 to each atom at a time. Also notice I didn't start with my central atom. By putting my other atoms all around it, it already was maxed out at its octet with those electrons in the bonds. But on top of that, if I needed to, I could have shared in one of these pairs to make a double bond at the end. We don't even come close to needing to do that. So I count up my octets on everything. I have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8. Silicon has 2, 4, 6, 8. Everything has an octet, so things are looking good here. I don't have any charges on this one, so this would be my final structure for it as far as the loose structure goes. Now remember, this is flat land. We do not yet have this drawn as a 3-dimensional molecule.